Okay guys, in this video we're going to go into a little bit deeper into these different orbitals or these areas of probability in which the electrons reside within our quantum mechanical model. So this is kind of part 2 of our little video series here. So in our last video we talked about how electrons do not orbit, but instead they are orbitals or areas of probability. And there are 4 types of orbitals that we need to work with. So the first type and the simplest type is called a sharp orbital, which we just designate with an S. So the S orbital is spherical in shape, and then if you have on the first energy level an S-shaped orbital, it's a certain diameter. On the second energy level, S-shaped orbital, it would just be a bigger sphere. Okay, so they just kind of get bigger as you go. Because the S-shaped orbital only has one orientation to it, it only can hold 2 electrons. Now, the second type of orbital is called the principal orbital, and we call that just designated as a P. Okay, so we call those P-shaped orbitals. If you notice, in a P-shaped orbital, you have kind of a dumbbell look to them. And within P-shaped orbitals, you actually have 3 different orientations. Or you have the PX, the PY, or the PZ. Okay, so because there are 3 different orbitals within this shape, okay, that allows for 2 electrons in all 3. So it's 2 and 2 and 2 for a total of 6 electrons in the P-shaped orbitals. Now notice they're not spheres. Okay, so again, the complexity of this gets much higher than what we saw in the planetary model, where just we had nice rings and orbits. The third shape is a D shape, which stands for diffuse. Now the D shape, if you look, even gets more complex, where now we're dealing with 4 lobes coming off in both the X, Y, Z planes, and then a different orientation within that, and then finally this kind of weird one down here, which we call DZ squared, which is basically 2 lobes with a kind of a donut around it. Okay, by far the coolest one. So within the D orbital, because we have 1, 2, 3, 4, 5 different orientations to it, or 5 different orbitals within this shape, we get a total of 10 electrons that the D orbital can hold. Now the last one gets kind of crazy. Okay, so F-shaped orbitals, you have all sorts of different lobes coming off, double rings over there. It just kind of gets a little bit messy to a point where we are definitely not going to try to draw on this thing. Okay, but there is 7 different shapes to it. So with 7 different shapes times 2, we get 14 total electrons that can go in there. So I want to take a second here to go to a program called Atom in a Box. And what Atom in a Box is a piece of software that someone wrote. I don't know really who did. But what it does is it shows us the actual wave equation from Schrodinger. Okay, so here's Schrodinger's wave equation. Okay, this is just for a hydrogen atom with a single electron, by the way. So here's his wave equation. So what Schrodinger did is he actually developed the math or the equation behind that actually gives us these areas of probability. Okay, and right now if we bring this down to its simplest form, here is the 1s orbital. If we go up to a 2s, you see it has the 1s inside of it and then the 2s region outside of it. So the area, the white areas are those areas of probability. 3s, 4s, 5s, 6s, 7s, and so forth, those different orbitals. Now as you notice, the math gets much more complex as you get higher and higher as you work. Notice on the first energy level, all we can get is an s orbital. But if I move up to the second energy level, a 2 here, now I'm allowed to have the s-shaped orbitals and p-shaped orbitals. So here's your p-shaped orbital to it. Now within p we have the x, the y, and the z. Okay, so we have all 3 orientations within the p-shaped orbital. Now on the third energy level we go to, I can now get not only the s, the p, but I can also get the D-shaped orbitals within this. And again, the D has 1, 2, 3, 4, 5 different shapes to it. Now, as we get higher, we can keep on going, and you see that this complexity here gets much more complex as you take a look at this orbital shape, these diagrams. Again, we're not going to be drawing these things, okay? The idea is just realizing that the location of the electrons is much more complex than we ever had thought before with the planetary model. But we can map them out by just identifying which electrons are sitting in which orbitals, and we'll use a numbering system for that instead, okay? And the way that we map that out is something called electron configurations, okay? So within electron configurations, there are actually 3 rules that we have to follow, okay? Those 3 rules are Aufbau Principle, Exclusion Principle, and Hundra Rule. So we're going to go through those 3 rules in this video, and then we're going to break again and have a video that gives us a little bit more detail on how to actually do them, okay? So the Aufbau Principle. This one makes perfect sense. It's the same deal as a planetary model. Electrons fill from lowest to highest energy. Okay, so they go from the first to the second energy level, the third, the fourth, and so forth. Notice how now, because we have orbital shapes, we have the S and P designation. So S is lower energy than P, and so forth. Also note that once we get into the third and fourth energy levels, and fifth and sixth, if they were shown here, that there's actually some overlapping that happens. So when we get to mapping these out, we're going to have to deal with this overlapping a little bit, so we make sure that we do sequence in from low to high energy. Second rule is Exclusion Principle. Exclusion Principle tells us we can put the maximum number of 2 electrons in any one orbital. Okay, we call these electron pairs. It's allowed to happen because these electrons have different magnetic spins to them. So imagine having 2 bar magnets. You can put them next to each other if you make sure that the south pole is lined up with the north pole, but you could not put them next to each other if the north poles were lined up together, kind of idea. Okay. So because the S-shaped orbital only has 1 orbital, it can get 2 electrons. Remember, P had 3 of them, the px, py, pz, so it gets 6. The D has 5. dxy, dyz, dxz, dx squared minus y squared, and of course our favorite, dz squared. And dz squared is our 5th one, so for 5 orbitals it gets 10 electrons, and then 7, or the F has 7 different orbitals, so it gets 14 electrons with it. Okay, so each shape can hold a different number of electrons, but each individual orbital, the px, the py, the pz, the dyz, the dz squared, still holds that number, or that magic number of 2 inside it. Okay, next is Hundra Rule. So Hundra Rule says that we had to fill our electrons in the most stable manner. Okay, now the most stable way to fill electrons is to half fill each orbital first and then go back and pair things up. Okay, so if we take a look in terms of diagramming these things out, if we were working with, let's say, oxygen, and we come over here to oxygen and we click on oxygen, you notice, if you kind of zoom in on oxygen, that it has 2 arrows here, and then 2 arrows here. Each arrow represents an electron. And then over here, we have 2 arrows and 1 and 1. Okay? And that comes from the fact that when you fill these different electrons into these different orbital boxes and these different shapes you can see kind of flashing on the screen here, that you want to half fill the P's before you start to pair up. So if we go back to nitrogen, you notice how nitrogen is 1, 1, and 1 because it half fills it. Okay? Oxygen has more electrons, so oxygen has to pair 1 up. Fluorine would have to pair another 1 up. Neon could pair all of them up. Okay? You go down to silicon and you see again it's 1 and 1 and it's trying to half fill. Then you go to phosphorus, it half fills them, and then sulfur starts to pair them up, and pair them up. Okay? So that kind of gives you an idea. And of course, here's all our different shapes that go along with these different orbitals. Here, okay? So that is Hundra Rule. Okay? This comes to play a little bit later on in our unit when we start talking about electron configurations and building them in terms of some of the exceptions that we go into there. Okay? Now, we're going to stop here, and then in our next video, talk about how we're going to use the periodic table to actually start to map out these electron configurations. All right, thank you.